we continue with our study of context-free languages. So far, we saw that context-free languages are languages which are generated from context-free grammars. So, to show that some language A is CFL, context-free language, we give context-free grammar G such that language generated by that grammar is equal to A, right? This is how we, and we saw that there are special types of grammars which can also generate A minus epsilon. The grammars in Chomsky normal form and grammars in Greibach normal form. To show that a language A is not CFL, what do? We use pumping lemma for CFLs. See, there are two pumping lemmas. There is a pumping lemma for regular languages and there is a pumping lemma for context-free languages. So we use pumping lemma for context-free languages. This is what we saw so far. Now, what we will do is, today we will study what are called the closure properties of context-free languages. So, here are some closure properties, but we can state it briefly as follows. CFL, context-free languages, are closed under the operations of union, catenation, reverse, Kleene closure. At least these four are true. So what do we mean by saying that CFL are closed under these operations? To show that CFL are closed under union, basically we have to show the following theorem. If A and B are any context-free languages, then we should show that A union B is also context-free. So union of any two context-free languages is context-free. In that sense, we can say that the class of context-free languages is closed under union. Similarly, we can talk about closure under reversal, closure under catenation. That is, if A and B are context-free languages, that catenation A dot B is also context-free. And if A and B are any context-free language, if A is a context-free language, then A star is also context-free. So these are some properties that hold for context-free languages, but we are going to see proofs of some of these, right? And how do we show that if A and B are context-free languages, their union is context-free? Let me give the proof. We can't give the language directly. Context-free languages are given by their grammars. So we will assume that we are given two languages A and B by means of their grammars G1 and G2, context-free grammars G1 and G2. And these are the two grammars. Now we will assume without loss of generality that the set of their non-terminals is mutually disjoint. That is, the non-terminal names used in grammar G1 are different from the non-terminal names used in N2, including the start symbols. The start symbol of this one is S1, start symbol of this is S2. If this is not the case, what we can do is we can rename the non-terminals symbol by another non-terminal symbol everywhere in the grammar, on the left hand sides as well as right hand sides, and we'll get a grammar which is equivalent. So this is easy. Okay. Now given grammars G1 and G2, what we do is, in order to show closure under union, we will construct a new grammar G, right, using grammars G1 and G2 which are given, and the construction of the new grammar is given here. What we will have in G is, all the non-terminals of G1, all the non-terminals of G2, that is N2, and one fresh new non-terminal called S. The set of terminals is sigma. We will define the set of productions of G, and this fresh non-terminal S that we introduce will become the new start symbol. And what will be the productions of our new grammar? Well, we will include all the productions of this grammar P1. We will include all the productions rules of grammar G2, and we will add one more rule which says S goes to either S1 or S goes to S2, right? So this is how we construct this grammar G. And then it's not a very difficult proof, but we can show that the language of this grammar G that we have just constructed is union of the language of G1 and language of G2, right? In that sense, we show that context-free languages are closed under union. Now, how do we show that this constructed grammar LG has same language as this? Well, we can show it. This is an equality. We say that the left-hand side set is equal to the right-hand side set. So we have to say one, we have to show containment in both directions. First, we will show that if language belongs to G, then it either belongs to G1 or it belongs to G2. Consider any derivation in grammar G. So a derivation in G will look like this. You will have to start with the start symbol, and then only thing you can do is you can either rewrite with S1, and from this you can derive some string X, right? If the derivation is of this form, the first rule always has to be of the form S goes to either S1 or S goes to S2, because this is the start symbol and one of them. If the first rule is of the following form, then and the subsequent derivation derives X, then it is easy to see that this is in grammar G. Then we have S1 derives X in grammar G1. Therefore, X belongs to language of G1. If S derives S2 first, and then this in grammar G leads to some string Y, then it is easy to see that S2 in grammar G2 derives Y, because we can only apply rules of grammar G2 here, because the symbols of G1 are disjoint from symbols of G2. Therefore, Y belongs to LG G2. And we are done with this. So this is the proof that any string which is derivable in G belongs to either language of G1 or language of G2. And converse is also easy to show. Suppose there is a string which belongs to language of G1, then there will be a derivation like this. S1 goes to X for that string, and then we can have a longer derivation which says, okay, so let me say converse. Let S1 derive some X in grammar G1. Then we have S goes to S1 is a possible rule, and then within grammar G, since all the rules of G1 are included in G, we can do the same derivation here and we can derive the same string X. Therefore, any string that belongs to LG1 belongs to LG, and similarly for G2. So we have finished the proof that these languages are equal. I hope that is clear to you. Okay, this is one proof. Okay, I'm going. So you will have to see this writing on the so let me do one thing. Let me add a page. And let me do one thing. From the page before, let me copy this part and put it there, because otherwise it will disappear. Okay, so this is the proof for union, right? So we have this. Okay, so this is the proof for that part. Let me draw a line here so that you will remember this when the first part disappears. Okay, next property. Okay, now we want to show closure under catenation, and we give a construction here which says that if we have grammar G1 for the language A and grammar G2 for language B, then the catenation of A B is recognized by this new grammar that we construct, which is given here. So again, like before, we have this non-terminals of the first one, second one, and a few fresh start symbol. All the productions of P1 as well as P2 are included, and you have this production which says S goes to S1 S2, right? Then my claim is that the language of G is same as language of G1 dot language of G2, right? So consider, now we have to show that the two sides are the same. So first assume that we have a derivation in G. So we start with S, and then in grammar G you rewrite this as S1 S2, and let's say we do a leftmost derivation. So after some number of strings, by leftmost derivation we will get rid of this everything that can be done on S1. So we will get some string X S2, and then by some derivations, this is in grammar G, this is all in grammar G, right? We get XY. This, a leftmost derivation from S will look like this, right? Right? So in that case, what can we show? Then we have the following derivation. S1 derives X, because we have used only the, rewritten the symbols generated from S1 and converted it into X2. We will have in grammar G1, S1 will go to X, and similarly from this S2, we will have derived X, because this X part does not affect how we derive Y from S2 part. So following property, because of context freeness, we have the following property. Similarly, if you have a derivation like this, then we can, so what I can write down is in blue, if this is the case, if and only if this. So if you have a derivation like this, then we have derivation like this, and if you have derivations like this, then we have derivation like, and hence these two are equal. So that is the proof that closure under this thing. So again, let me try to store this part so that it's available to you for your future reference. Okay, so copy, and then let me go to the previous page, and let me do paste, and then move it down. So I'll write down catenation. So these are the proof parts. Okay. Now let me go ahead. The third property is, oops, we have one, it jumped to the end. Okay. And here we give construction of a grammar which gives closure under cleany closure. So suppose we have a grammar G, for language A, we have this grammar G1 for language A, then for language A star we can construct a grammar G, which is given here. So it has again a fresh non-terminal S. We have all the productions of G1 here, and we have this extra production which says S goes to S1S or epsilon. This is, then we can show that the language of G is equal to language of G1 star. So it's an exercise to you to show that this is true. Okay, if there is difficulty, you can ask me in the doubt clearing session. So we have constructed this, and then what do we do about reverse? How do we show that language of closure under reverse? How do we show? So let me again draw this thing. Under reverse, Well, what we do is we reverse every transition. So I'll give you an example. If my G1 has following production, S goes to A as B or epsilon. So which language does this generate? Ls is equal to A raised to n, B raised to n, right? In order to generate reverse of this language, we reverse every production. So I will write that. So my G has following productions. S goes to reverse of this string over terminals and non-terminals, which I'll write as B S A. And then I will reverse this string. So reverse of epsilon is epsilon. And then my claim is that this is language of G1, and this is language of G will be Bn An. So by reversing every production, you will get the reverse language. Okay, so we have shown all these properties. Now so upshot of this is we have proved that context-free languages are closed under union, catenation, reverse and Kleene closure. Regular languages were closed under some additional operations, particularly intersection and complementation. What happens in case of context-free languages? Let us see. There's some noise here, so let me shut the language. So it turns out that context-free languages are not closed under intersection. What do we mean by they are not closed under intersection? We mean that if A and B are context-free languages, then their intersection, A intersection B, need not be CFL. That is, it can be CFL, but it need not be CFL. Or in other words, to show non-closure, we have to give a counter example. That is, we have to show two context-free languages A and B such that A intersection B is not CFL. Sorry, there is a mistake here. It should be written as CFL. Okay, so what we are showing is there exists at least two context-free languages A and B such that their intersection is not CFL. Okay, so we give a counter example to closure of CFL under intersection. Now, let us try to give such A and B. So choose A as the language, A and B and CM. That is, we have strings of the form A star, B star, C star, where number of A's is equal to number of B's, but number of C's can be different, right? So M and N have no relation. This is my language A. My language B is A raised to M, B raised to N, C raised to M. So here number of B's and C's are equal, but number of A's can be arbitrary. So what we have to show is this language is A and B are CFL. So exercise is give grammars. Give CFG for the languages A and B, and that's a homework exercise for you. Give CFG. Okay, to give one CFG for A and one CFG for B. So we know that these two languages are context free. Now what is their intersection? You can easily see that in this there are all strings where number of A's and B's are equal, but C's is arbitrary. Here number of B's and C's are equal, but A is arbitrary. When you take the intersection, you get the language, you know, where number of A's is equal to number of B's is equal to number of C's. And we have already shown that this language is not context free. How did we show this? We showed this using pumping lemma. So this is a counter example which shows that context free languages are not closed under intersection, an important property. What about complementation? It turns out that context free languages are not closed under complementation either. And we will give this proof by contradiction. Let's assume that for every context-free language A, the complement of A is also context-free. Okay, if that is the case, let AB be some arbitrary context-free language. We can write down their intersection using set theory as following. This is nothing but De Morgan law, right? Law. It says that A intersection B is exactly equal to the right hand side expression. This you know. This comes from set theory. But if context-free languages are closed under complementation, then if A is context-free, we are given A and B are context-free, then this underlined expression is context-free, its complement is context-free, B is context-free, so this is context-free. Now these two blue languages are context-free, so their union is context-free. The red language is context-free, and when we take the negation of this context-free red language, we get a context-free language. So RHS is, because union and complementation are, we have assumed, are closed under complementation. Union we have already proved, but this we have assumed. RHS would be closed under context-free. So this would imply that context-free A intersection B is also context-free. This contradicts that CFL is not closed under intersection. This would imply that for every context-free language A and B, A intersection B is context-free. But we already showed that this is not the case. So our assumption, that complement of a context-free language is context-free is wrong. And so we conclude that there are at least some languages for which complementation is not context-free, right? So we have considered the closure and non-closure properties of context-free languages. Okay, so you should know these properties. We will also consider some decision problems. If you are given a grammar, we want to analyze this grammar and come up with some conclusions. Suppose you are given a grammar G and a word X belonging to sigma star. We want to find out if X belongs to the language of G. This is the question we want to answer, right? And we want to do this algorithmically. That is, we want to design a terminating program which will answer this question. Now there are some very famous algorithms for doing this. If the grammar was in Chomsky normal form, we know that given the length of X, there is a bound on how long the derivation of X can be. So we can explore all possible derivations from the start symbol of that particular length and check whether X is derived. But this is a very inefficient algorithm. There can be exponentially many derivations from the start symbol of length n, and so this is not, what I said just now is not an efficient method. There is an algorithm called CYK algorithm. We will not study this algorithm here, but this runs in time order n cubed where X is of length n. So in order to check whether a string of length n belongs to the language of a grammar, we have this algorithm, CYK algorithm, which takes order n cubed number of steps, okay? And it uses some sort of dynamic programming. Now I'm not going to do this algorithm, but it's enough for you to know that there is an algorithm which checks for membership problem, whether X belongs to LG. So this is also called membership problem. So membership problem is decidable, right? Yet another related problem is that given a grammar G and a string X, we want to not only know whether it is derivable, but we want to derive its parse tree. Parse trees are very, very useful because very many computational problems about context-free languages require their parse trees to be constructed. For example, if you want to convert English to German, given an English sentence, we would construct its parse tree. We would transform the English parse tree to German parse tree, and then we would take the yield of the German parse tree to get the equivalent German sentence. So, in translation, in compilers, similar things are done, and constructing a parse tree for a given word X under a context-free grammar G is very widely used. What is the problem? Suppose you are given the grammar G as S goes to ASB or epsilon, right? And you are given X equal to AABB, right? So what would be a parse tree for this string in this grammar? We would start with S and we would rewrite this as ASB, and then this S we would rewrite as, so this A will remain as it is, ASB, and this B will remain here, And then what would happen? This S we would rewrite by epsilon. So this A would remain as it is, this A would remain at, this S will write as epsilon, this B will come down, this B will come down, and we will have derived the string AASB. So this is the parse tree of this language, and the question is, given this string and this grammar, we want to generate this parse tree, or to say that there is no parse tree which generates this string, right? This is called parsing, and it's very widely used. Now, constructing parse tree of a given context-free grammar is difficult. So there are special kinds of context-free grammars, and there are special subset of context-free languages for which generating parse tree becomes easier. Firstly, these languages are called as deterministic context-free languages. We will not give the definition here, but there are special grammars such as LLR grammar or SLR grammar or LRK grammars for which there are efficient algorithms which will generate the parse tree of a string from it. And they will take not cubic, the time taken to generate the parse tree will be linear in the size of the string. So that most of the programming languages that you use today, like C or Java or Python, they belong to they are generated by this special purpose grammars for which constructing parse tree can be done efficiently. And so if you give a 1,000,000-line program, the construction of parse tree in its compiler will roughly take time proportionate to million. If you use CYK algorithm, you would require time proportionate to million cube, which is too much, and no compiler would be able to spend so much time. So these are the languages which are efficiently parsable. Okay, we will again not do this theory of parsing this kind of grammars, but if you do a course on compiler construction which takes on from what we have been doing for context-free languages, you will study these algorithms. In fact, for this developing such efficient algorithms, Eho and Ullman, received this year's Turing Award, the highest award in computer science. So these are very influential algorithms, and one of our textbooks is written by Eho, Hofcroft, Ullman, right? So they are the authors of our textbook. They received this year's Turing Award for developing such algorithms. You should know these facts. You don't have to study these algorithms. Okay. Also, given a grammar, we want to check whether the language of the grammar is empty. That is, it does not generate any string. And this is very easy. I leave it as an exercise for you to do. If you are not able to solve it, ask in the doubt section, and then I will be able to do it. So emptiness of context-free grammars is decidable because there is an algorithm, terminating algorithm, which given the grammar will tell you whether its language is empty or not. Okay. On the other hand, if we ask for the universality question, that is whether the language of the grammar is equal to sigma star, that is every string over alphabet sigma can be generated or not, this problem is undecidable. There exists no terminating algorithm which given a grammar will be able to do this analysis and answer this question. So there will always be some grammars for which this question will not be answerable by a computer algorithm. No matter which algorithm you give me, there will be some grammar for which it will not be able to correctly answer this question. So this is a rather hard question, and in the later part of the course we will show how undecidability of problems will be proved. That the fact that there are problems which cannot be solved by any computer algorithm is surprising, and this is one of those problems. Okay. So we have considered some of these problems. So what we have done today is some of the closure properties of context-free grammars. We have seen some non-closure properties, and we have looked at some decision problems for context-free grammars. That is all I wanted to say, and I hope you will study this material so that you understand, context-free languages thoroughly. Thank you.